Good morning, everyone. Welcome to our ICP-OES analysis of metals and sulfur in oils using aqueous-based standards. It's great to have everyone join us this morning. My name is Amanda Miller. I'm the Director of Client Operations here at Inorganic Ventures, and I'd like to also introduce our esteemed guest speaker today, Madeline Gozzi. She is an R&D chemist here at Inorganic Ventures. She's been with Ivy for over 30 years now, so we are very lucky to have her presenting to everyone today. She's been working very closely with Dr. Paul Gaines, as well as Mike Booth, our Research and Development Director, Technical Director here at Ivy on these standards. So just a couple housekeeping things as we're waiting for more people to attend the webinar. If you have any questions throughout the webinar, please be sure to put them in the Q&A box. You can find that down at the bottom of your screen. Type those questions in. We will hold all questions till the end of the webinar, and we'll address those one by one. I'll read them out to Madeline and have her answer the questions at the end of the seminar. If you have any technical issues, also just put that in the chat and we'll address those as best we can in the meantime. But without further ado, I will now pass it off to Madeline. Thank you, Madeline.
Thank you, Amanda. Thank you so much. And also thank you to Grace Hurst for setting up these wonderful webinars for us. Well, good morning. I'm so happy that you're here. Today, I'm going to be telling you about our development of our hybrid aqueous organic solvent standards that are used for testing metals in oils by ICP-OES. Just to let you know, in case you have to jump off the webinar early, you can send us your questions at info@inorganicventures.com. And you will also find a link to a form in the chat where you can ask us to get more information about the product that you're going to hear about today. So we will begin. Just in case you're not familiar with Inorganic Ventures, we are a certified reference material manufacturer. That is, we make solution standards for most elements in the periodic table, single element solutions, multi-element blends, many custom solutions that are requested by our customers. We make pH standards, conductivity standards, titrants, and also reagents. Now, why did we decide to look into a new approach to testing metals in oils? This idea came from Dr. Paul Gaines, who is the founder of Inorganic Ventures. Many decades ago, Paul spent a lot of time while he was with Exxon Research studying and working with organometallic standards and wear metals in oils testing. Traditional organometallic standards are largely made from metal carboxylates and metal alkyl aryl sulfonates. What Paul found was that there could be stability issues, long-term stability issues with these materials. So we know that our aqueous metal standards are extremely stable. We have up to 5 years stability when these materials are in the original containers in foil closed TCT bags. So what he wanted to do is to use our aqueous standards and find a way to combine that with, an organic solvent that allows for testing metals in oils. So we're going to look at this method development. Initially, as I mentioned, our starting point was that we already have these aqueous metal standards that are in dilute acid. Our goal was to develop an organic solvent in which the aqueous metals in dilute acid would be miscible and stable. The organic solvent at the same time needs to be able to dissolve oil samples and all of the analytes in those oil samples. When we were looking at the organic solvents that are currently and traditionally used for testing metals in oils, we saw they're quite hazardous. So we wanted to find a solvent system that would be better for the health of the analysts and also for our environment. After a lot of work, we did find a suitable solvent system. Happily, we did find that we could make this solvent primarily at this point from green and sustainable resources. The aqueous standards that we have are miscible and stable in the solvent, and traditional oil standards and the oil samples are miscible and stable in the solvent. So sorry. To ensure the stability of our aqueous calibration standards, we needed to split them into two groups. 22 out of the 27 elements that we're testing are in dilute nitric acid. And you can see in this group that we have included sulfur. We'll talk about that a little bit later. 5 of the elements are in hydrochloric acid with a low concentration of hydrofluoric acid. In the final calibration standards, we are in dilute hydrochloric acid in these standards, and it is very, very trace HF. Our final solvent system that we're calling IV 77742 provides for the miscibility of the aqueous inorganic metal standards and the oil samples. We added cobalt and yttrium as internal standards to our solvent. This makes the dilution process of the standards and samples easy. It's a one-step process, and it is the same as what's currently done with the traditional organometallic standards. Also, each batch of our organic solvent, IV 77742, is tested for trace metallic impurities for all the elements of interest in the standards. We actually did trace metallic impurity looking at basically the entire periodic table, the way we do for all of our custom grade aqueous standards. Currently, we're doing stability testing on the organic solvent for the cobalt and yttrium components. So far, we have it certified for 6 months stability on the cobalt and yttrium. We are continuing that stability testing out to a year or more so that we can extend that certified stability time. It looks very good for the stability of the cobalt and yttrium in this solvent. So this method is calibrated to test for the total 27 elements using the 2 sets of calibration standards. We made, again, 2 sets of calibration standards. Each set has 6 standards in that set. 0 micrograms per gram, 1 microgram per gram, 5, 10, 20, and 50 ppm from the nitric aqueous standards and from the HCl standards. The matrix of the calibration standards after dilution is 1 to 10 weight to weight, aqueous to organic solvent ratio. And the working calibration standards contain 1% volume to volume nitric acid, and the second set contains 2% volume to volume HCl. Here you see a little schematic showing the dilution procedure for the aqueous standards into the organic solvent. You're just making a 1 to 10 weight to weight dilution of concentrates of the aqueous standards to give you the final concentrations that I mentioned. So you can see here that the aqueous standard concentrates range from 0 up to 500 ppm. 1 to 10 dilution is giving you the final concentrations of 500 down to 50 ppm, et cetera, for all of those calibration standards. Again, the PREP method replicates the procedure that is often used in wear metals testing laboratories. We recommend doing weight-to-weight standard preparations. We've also seen this in real-world wear metals testing laboratories where they dilute their standards, their organometallic standards, weight-to-weight into their solvent. And some of these labs do volume-to-volume dilutions of their samples. We'll talk about that again in a moment. So speaking of the volume-to-volume dilutions, the density of our solvent, 77742, is very similar to that of the oil samples. So with the densities being equivalent, it's acceptable to dilute the samples, the oil samples, weight to weight or volume to volume into the solvent. Cobalt and yttrium internal standards are present in this solvent, IV77742, which after dilution, the concentration of the cobalt is 15 micrograms per gram and the yttrium is 5 micrograms per gram. And that is in your calibration standards and in your samples. An additional benefit of this method, and this is something that was not possible to do with the traditional organometallic standards, is that we are able to offer sulfur as an analyte that can be tested with our hybrid standards. The reason you can't test for sulfur with the multi-element blends organometallic standards is because they are commonly made from the alkyl aryl sulfonates, the sulfonates adding large amounts of non-quantified sulfur into those solutions. So that precludes the analysis of sulfur. We have been able to use sulfur as a methane sulfonic acid, in our aqueous standards, which allows for the determination of sulfur in the oil samples. So now we're going to talk a little bit about the actual testing on the ICP, and I'm going to give you a little background on our instrument setup. In our lab, we use the Spectro Arcos 3 in radial mode, and the intro system were the twister, baffled glass spray chamber from Glass Expansion. We use a Guardian sample probe, also from Glass Expansion, and Solvaflex peristaltic pump tubing. In this slide, you see pictured the two nebulizers that we used. We used Texas Scientific Products Optimist Ultimate Nebulizer, which is made from Ultem plastic, pardon me, which makes it HF resistant. We also used, shown on the right, is the Glass Expansion Slurry Nebulizer. It's a concentric nebulizer made from borosilicate glass. We were delighted with the results that we got from both of these nebulizers. Both nebulizers are made for this kind of testing, for oils testing. Both of them have a high tolerance to particulates. Both of them, and this is what we were very happy about, besides the excellent results, the RSDs for both nebulizers were very low, ranging from less than 0.2% up to approximately 1% RSD. When we looked at real-world oil samples, they were also very good, most lines having less than 1% RSD for oil samples run at 1:10 dilution in the solvent. These are our measure conditions. The plasma power was set to 1400 watts. Coolant and auxiliary argon gas flows were those that are commonly used for oils testing. The nebulizer gas flow for the TSP Optimus Ultimate nebulizer was 0.9 liters per minute. That's the optimized gas flow for that nebulizer. And for the slurry nebulizer, 0.8 liters per minute. In oils testing labs, they are looking at extremely high sample throughput. Probably hundreds of samples each day need to be analyzed. So our goal in setting up the ICP-OES method was to get the best possible results with the minimum time per sample. An oils testing lab may have, we've seen time per sample from 1.5 minutes per sample all the way down with specialized instrument setups, 20 seconds per sample. What we did was we used a 3-second read time for standards and samples, giving a total of 60 seconds for total time per sample. We also tried an alternate 6-second read time per sample to see if that would give us some improvement. That gave a total read time of 75 seconds per sample. And we saw a minimum in marginally better results from the 6-second read time. Again, I'm pretty sure I said we did all this work in radial mode. We added the 1 microgram per gram standard to our calibration curves because we understood that for some testing of certain elements like aluminum, chromium, lead, and tin, they need to be detected at concentrations down to, this is in wear metals testing, they need to be detected in concentrations down to 1 ppm. So we wanted to have more confidence in our results at that low levels. So by adding the 1 ppm standard, you can see from the slides, and this is just one example, these are 2 aluminum lines. You can see clearly that the 0, the blank standard, which has the blue arrow pointing to it, is clearly different and cleanly different from the 1 ppm standard. The screenshot on the right is showing you the best aluminum line, which is the 167.078 nanometer line. That line gives you the best sensitivity and also the lowest method limit of detection. So just as an aside, we do recommend the 167 line for this work. So we're going to look at the method validation and the results. How did we validate our method? To validate the method, we used our hybrid aqueous organic solvent standard and tested a number of different organometallic CRMs and also NIST SRM 1085C as samples. The NIST, as you see here, is named wear metals in lubricating oil. The diluent for all of these samples was our solvent IV-77742, including the cobalt and yttrium at 15 ppm and 5 ppm respectively in the diluted samples. The organometallic single element sulfur, that is the first one on our list here, was tested to confirm the sulfur testing ability using our hybrid standards. We tested multi-element organometallic standards. You see different, from different manufacturers. So you see 26 element wear metal standards at different concentrations. And we also tested additive elements at 1,000 ppm. So we're going to continue and look at some of our results. Now, there are a lot of numbers here, so don't worry because you're going to be getting a recording of this webinar, you can look at the results in a lot more detail. In the next 4 slides, the results were generated using the glass expansion slurry nebulizer. In the last slide, you're going to see results for the NIST SRM using the TSP Optimist Ultimate Nebulizer. So looking at a little bit of detail on this slide, in the first column, you see the elements and the element line. These were the best lines. The results for each of those elements. Third column gives you the percent recovery. And the fourth column we included for interest, and perhaps this can help, the best internal standard lines for cobalt and yttrium. And you'll see in more detail, again, as you look at these, most of the elements were within 2% of their certified values when we tested this multi-element organometallic blend that was certified at 50 micrograms per gram. Next, we see the results from the testing of the 100 microgram per gram multi-element organometallic standard versus our hybrid standards. Again, most of the elements were within 2% of their certified values. I'm just going to mention that at the bottom of this slide for vanadium and zinc, I found that I did better not using the internal standard in the determination of the results. It was there, but I chose not to use it. This slide, we have the multi-element metal additive standard. This was at 1,000 micrograms per gram. Again, the percent recovery within about 2% of the certified values for most of the elements. I will mention this again, but just like in normal real-world labs, oil testing, no matter what the concentration of the sample, those samples are diluted 1 to 10. We did that also with all of these standards. So no matter what their concentrations, we diluted them 1 to 10 in our solvent. This slide here shows the results of testing the single element 1,000 ppm sulfur organometallic standard versus our hybrid standards. And the result here for the sulfur 182 line was within 0.3% of the certified value of that organometallic sulfur standard. This is the slide with the results from the NIST SRM 1085C versus our hybrid standards using the Optimist Ultimate Nebulizer. And as we look down our results, we see that most of them are within 2% of the certified values for this SRM. So next, we'll talk a little bit about our thoughts and the observations on our work. And I'm just going to take what's right here in the slide and just say it. The traditional organometallic standards tested versus our hybrid standards yielded largely results within 2% of those elements' certified values. Our organic solvent plus the cobalt and yttrium ensures ease and accuracy of standard and sample preparation. Short sample run times could be used to achieve accurate results and excellent reproducibility. Our solvent IV-77742 was also observed to be excellent for cleaning the intro system. It did a good job of washing out the residual oils. We also saw no carbon buildup on our torch injector when we were testing the traditional organometallic standards versus our aqueous organic hybrid standards. So what conclusions did we draw from our testing? And we'll talk a little bit about beta testing the hybrid standards and other applications. So the analysis of the traditional organometallic CRMs versus our hybrid aqueous organic solvent standards confirmed the accuracy of those hybrid standards. The stability of our aqueous standard concentrates is documented for up to 5 years when stored in unopened, sealed foil TCT bags. The organic solvent, and we're very happy about this, is primarily sourced from green and sustainable resources, lowering health hazards to both the analyst and our environment. The solvent is a great rinse solution for oils in the ICP introductory system. This is really important. Sample preparation method that we used is identical, actually, to the sample prep method that's often used in traditional organometallic oils testing laboratories. This was done deliberately to ensure an easy transition from using traditional standards. We also made sure that our method was analyzing for all of the elements that are prescribed in the ASTM methods for testing wear metals in oils on ICP-OES, that is D5185-18. And we did not use this method, but there is a D6595-16 is a rotating disc AES, but those are also the same elements that are prescribed for testing. Just going to go back to that for 1 second. So we used, just to emphasize, we used a common dilution of 1 to 10 for standards and samples in our diluent. The cobalt concentration that's in our solvent and when diluted to 15 ppm and the yttrium concentration are also familiar to oils testing laboratories. The 1 to 10 dilution of the sample into diluent is again the same. So at this point, I want to mention that that's the information we have for you for now. We hope that you might be interested in learning more about our method and trying out our materials. So we have test kits that are available to laboratories. Each kit contains a liter bottle of IV 77742, which contains the cobalt and yttrium internal standards. The kit contains 30 ml bottles of each of the aqueous concentrates that are used to make the calibration standards. You will also be getting the application note, which has instructions on making the standards and samples. You will get the white paper that is detailing this project with much more information than I could give you right now, and some other documentation which will help in your testing. This recording will be sent to you. The recording of the webinar will be sent to you after the webinar. If you're interested in getting a test kit, you can click on the link in the chat for the interest form, fill out that form and send it over to us, and we will set up a telephone or a video chat with you so we can discuss more, or we can do this by email. You can also email us with any questions about this or any other question you might have at info@inorganicventures.com, and we will get back to you as soon as we can to help you out. And just to let you know, we're currently exploring more applications for our hybrid standards and the solvent. We're looking at the analysis of biodiesel feedstock for metal contaminants and also XRF analyses of oils. I hope, and we all hope, that this webinar gave you some information about this new product. Here on this slide, you see all of our educational resources that you can scan, click on, and get more information and help from us here at Inorganic Ventures. Thank you for being here. Thanks, Amanda. I guess we're ready for some questions.
Yeah, great. There's a few questions that have popped in here. So first question, I saw in the white paper you referenced some ASTM ICP-OES methods. Have you looked at the ICP-MS? There is the ASTM D5110 application, which is similar in terms of sample preparation.
No, at this point, we have not looked at ICP-MS methods, but thank you very much for bringing that up, and we'll have to put that on our docket for the future.
Okay, great. Next question, where does this method stand with ASTM certification? Have you submitted this to ASTM as an alternate or new ASTM test method?
Thank you. That's great. And we are looking into this right now. We have not yet submitted this method to ASTM. Part of the preparation work for submission is getting the beta testing done and sending out the sample kits to various laboratories is going to give us data from these labs where they're using different instruments, where they're having to deal with their day-to-day work and see how our system compares to theirs. We're going to be using those results to help us get ready to submit this method to ASTM for approval.
Great. Then we just have a comment of someone that's absolutely interested in a follow-up about the biodiesel feedstocks as we generate more information on that. So we'll get back to you, Mr. Mann, with more information about that when we develop that.
Definitely. We're starting to work on it. We got some initial very good results, and we can talk about that more. Definitely.
Okay, and then just one other question. Can we make the calibration standards ourselves?
You will definitely be able to make the calibration standards. Now, just to define, the calibration standards will be the diluted aqueous standards into the solvent. So yes, you will be certainly able to make the calibration standards yourself because, for example, if you decided you wanted a test kit, we're going to send you the aqueous standard concentrates and you will dilute those into the organic solvent. Now, if you wanted to make the aqueous standards yourself, yes, you could do that. You can buy the single element solutions and make up the aqueous standards. You would need to get the organic solvent from us.
Okay, great. And then just one last question. We cannot use HF in our labs. What is the final concentration of HF in the calibration standards?
Thank you. That's very important. I mentioned that it was very trace. I didn't say what it was. It's actually the highest concentration of HF in the calibration standards is 0.06% HF. So it's very, very low. It's actually an order of, more than an order of magnitude, probably two times, not 2 orders of magnitude, but it's more than 1 order of magnitude lower than what is normally considered trace.
Okay, great. One more question. Let me get in
Yeah.
here and get that one. Somebody asked if this presentation is available. Yes, you'll receive an email in the next few days with a link to the recording of the webinar.
Mhm.
Okay, and I don't see any other questions coming in. So just a quick reminder to everyone, there's more information in the chat, info@inorganics.com if you would like to email us if you have questions or you are interested in receiving the test kit that Madeline spoke of. Also, Grace was gracious enough to add some additional resources. There's a Bench Boost podcast, a white paper, and the application note. There's links to all of that also in the chat if you'd like additional resources or additional information. But with that, thank you so much, Madeline. It was very informative. Appreciate your
Thank you,
time.
Amanda.
Appreciate all of you joining us. It's great to see so many familiar faces attending our webinar this morning. If you need anything else, don't hesitate to reach out to us. And again, the recording of this webinar will be emailed out to everyone that registered in the next few days. So thank you again, and we hope you have a wonderful day. Thank you.
Thank you. Bye.